Thank you for coming and thank you for joining online. My name is Maciej Lipiński. I will speak louder. Okay, my name is Maciej Lipiński, and together with my colleague Adam, we are coming from CERN in Switzerland slash France. And just next. Okay. And today we'll be speaking. I will tell you a few words about what is CERN and how we help push limits of science, and then doing so, we also push limits of technology. And then one of the examples is White Rabbit. So we'll be speaking about White Rabbit and show you a demo of White Rabbit, how it works. And then one of the end nodes of White Rabbit is ÜberNIC. So you will also hear about ÜberNIC. Okay. So CERN is a scientific collaboration and the world's largest particle accelerator. So a laboratory that works on particle physics. And this is done to understand the most fundamental laws of universe, of physics, and to answer some very basic questions like, for example, why are we made of matter, not antimatter? Or why different types of particles have different mass, for example. So this kind of basic questions we are trying to answer. And by doing so, we are pushing not only the limits of science, but also engineering and technology. So CERN is primarily a European organization with 23 member states, but we collaborate with institutes and companies all over the world. Now, as I told you, we are pushing technology to push science. And this is because we are doing experiments for which we cannot buy, to conduct them, we cannot buy off-the-shelf electronics or devices to perform them. So as much as we can, we do buy off-the-shelf stuff, but very often we need to develop our own technologies and capabilities to build new technologies to perform scientific experiments. And this is done in 3 different key areas in accelerator science. So we are accelerating particles that we later smash, and we make pictures of these collisions in huge detectors. And this creates a lot of data, and this data needs to be processed. So we are also basically pushing the computing science. So just a few examples of the technologies that we create at CERN and we use at CERN. So we are operating many accelerators, among which is the biggest accelerator in the world, which has 27 kilometers circumference. It is located 100 kilometers below the ground, and it is running superconducting magnets, with the magnets being at super low temperature, meaning 1.9 Kelvin degrees, so almost zero absolute. And we need to have high vacuum in the pipe, which is 27 kilometers, to be able to run a beam of particles and not to collide with some debris that are inside, because there would be bad vacuum. Then once we accelerate a beam, we collide beam in collision points around which we have gigantic detectors. So those are big, you can see it as 3D cameras that are 100 meters long and high, and located under the underground, 100 meters underground. And those are the detectors basically record different characteristics of the beam. It's like taking a picture, 3D picture, just that we take this picture for 40 million times a second. So every 25 nanoseconds, we take a picture. And this is quite a lot of data that is filtered, but even after filtering, we end up with loads of data. And to cope with the data, we created worldwide LHC computing grid, which is used to store, distribute, and process and analyze the data. It includes 1 million processing cores in 170 data centers and 42 countries. So what we do, we produce data and then we distribute it over, to many countries over network, both for redundancy and also for computing power. So this amounts to more than 1,000 petabytes of data. So the question is, okay, we are pushing the technologies and creating new technologies. The question is, can we use it for our everyday lives now? And the question is yes. So CERN, the technologies developed at CERN are used in different areas, from healthcare through environment, digital, aerospace, and quantum. And just to give you very few examples that are relevant, one example is that to process all the data, we are pushing the machine learning and AI algorithms to FPGAs to make the learning and computing faster. And this is currently studied together with Volvo to use it to digest the information from sensors in the cars so that we can faster react to what happens in intelligent cars, let's say, and not only. The other technology that was created at CERN and now is used outside is White Rabbit. So this is the technology that we want to focus today. And White Rabbit technology was created at CERN to control and synchronize devices in accelerators. So what you see here is our chain of accelerators, which include the biggest accelerator, which is 27 kilometers. So this ring is 27 kilometers. In the accelerator, we are running, we have a beam that travels at the speed of light. So we need to control a beam that travels at the speed 0.99999 of the speed of light. Whereas the signals to control devices in the accelerator travel at 2/3 of the speed of light. So we cannot control the beam and the devices in a classical way where you basically say that something should happen and then the signals are distributed and it happens. Because the difference of distances between the controller and different devices makes such that they arrive nanoseconds or microseconds in different time. So what we are doing, we are basically synchronizing all the devices in accelerator to within a nanosecond. And then we are sending in advance information what should happen at a given time. And then these actions are executed at this time precisely. So we can execute an action in two different places in accelerator at the same time to within nanoseconds, thanks to that. And this is the primary goal of creating a White Rabbit. Now, in general, White Rabbit technology, it is based on well-established standards, meaning Ethernet and IEEE 1588, so precision time protocol. It provides sub-nanosecond accuracy of synchronization. And this means that if you have a network of few thousand devices connected through many switches, we will get all these devices synchronized to within 1 nanosecond. On a single link, which is up to, in case it's up to 10 kilometers, the accuracy will be below 20 picoseconds. And on longer links, it might vary depending on the technology. And we have White Rabbit links of more than 1,000 kilometers in deployment. In terms of precision, we can do easily 2 picoseconds precision below. And important thing about White Rabbit is that it's open source and commercially available. So the sources for the software, for the FPGA code, for the hardware, everything is available for anybody to have a look, to produce, to use for free by us. And yet there are companies that sell these devices, take the sources and basically sell the devices for price. And now White Rabbit was developed as an extension to a standard, IEEE standard, precision time protocol. So basically improving some limitations of the standard. And since it turned out that those improvements are interesting and useful, those improvements were incorporated into the standard. So now whatever we added on top of the standard became part of the standard. So we standardized White Rabbit, in other words. Now, as I told you, White Rabbit is sold by companies. So you have, for example, here, 5 vendors of White Rabbit switches. So the switches are the devices that you see on the table. Those switches are sold by Safran. Safran is from Spain. Syntec Technology in China, Cryotech in Poland, OPNT in Netherlands. And then we are working with GMV in UK. Also, they will be selling the new generation of the switch. In terms of the end devices, there are many vendors, but I will just mention one, which is ÜberNIC. So you can basically, ÜberNIC, one of the features that it implements is White Rabbit. But there are many other endpoints, not NICs, that also implement White Rabbit. For the time being, mostly for scientific applications and measurement and instrumentation. In terms of applications outside CERN, there are plentiful. I just mentioned a few examples which might be relevant and interesting for you. First of all is space. And actually, we are not sending White Rabbit and using it in space. However, the GNSS, any GNSS has two segments to it. You have the space segment with satellites and the ground segment, which is controlling the satellites. So you have in different places facilities that check whether the time provided by satellite is correct and then also correcting it. The entity responsible for Galileo is ESA, is a European Space Organization, and they've been evaluating White Rabbit to synchronize the ground segments between different countries. In finance, White Rabbit is used. You have here the examples. Deutsche Börse, German Stock Exchange, is selling White Rabbit time as a service to the high-frequency traders. And it is also using on their side White Rabbit to monitor the traffic. So they have tabs with the timestamp in and out traffic, and those tabs are synchronized with White Rabbit devices. Jump Trading is using White Rabbit for performance monitoring. Optiver is also testing White Rabbit for synchronization between facilities. And in the general financial sector, ÜberNIC is also a player which supports White Rabbit. White Rabbit was started as a synchronization technology for up to 10 kilometers, but very fast there were applications for longer distances, and I would just mention a few of those. So European organization is, as many others, have identified the limitations of GNSS-based synchronization. And they made a call for alternatives for position, navigation, and timing, meaning they basically asked what would be the technologies and solutions that could be used to have backup or replacement of GPS over the ground over fibers. And in the responses, they saw a lot of proposals, and many of those were based on White Rabbit. Another thing that is now happening in Europe is that we are thinking about having European-wide time, official time. So now each country has its own official time, and they compare between themselves. But in EU, we are now thinking to actually have a pan-European network which provides time as a service, which is European time. And here also White Rabbit is considered seriously. Another use case is Sweden net node. So they have implemented synchronization using White Rabbit in 2021. And NetNode is a leading provider of interconnection in Sweden. And they run a White Rabbit in a live network between Stockholm and another city on a link of over 400 kilometers. And then they explain very nicely in this Q&A what is White Rabbit and why does it matter for high accuracy time services. You can follow the link to have a look. Another use case in Italy. So Italy is one of the countries that is using White Rabbit to distribute time internally. So the official time is distributed over entire country, and then to some places already over White Rabbit. And one of the places which uses White Rabbit to take the official time of Italy is Milano's financial district. So they run a link between the place where they realize UTC Italy to the Milano district. And they also have a connection of 1,800 kilometers using White Rabbit. So this part of the presentation was a general overview of White Rabbit, how it is used and where it comes from. Now I have another part which is more about how it works in more details. So any questions before I go to this part? Perfect. Any questions from the online, if you still are there?
I'm still here. I don't see any questions in the Q&A, but I'll keep an eye.
Okay, shout if you have some.
Yeah.
So then if we speak about White Rabbit, we speak about synchronization. So I have one slide about what is synchronization in a nutshell and how it is important and how it evolved over time. So first of all, we are speaking about synchronization in the context of synchronizing devices over a network. So we have two, we have two PCs connected over a network, And if you look at their clocks, they both show the same time. That means that they are synchronized, right? So they show 11:50 roughly. Now, if you look at the digital clock, we will see that actually one of them is showing 11:50 and 0 seconds, and the other 11:50 and 1 second. That means that they are synchronized to within 1 second. So the inaccuracy or the accuracy of synchronization is 1 second. Okay. And it's always the case that devices are synchronized to within some accuracy. They are never perfectly synchronized. You can go to attoseconds if you want to have some imperfections. So then just to imagine what is, so 1 second we can comprehend. This is 1 second roughly. But in industry and in the world, essentially we care about milliseconds, microseconds, nanoseconds. And it's quite difficult to imagine what it is. So I try to explain. If you look at the, if you take light, so if you shine a laser onto a moon, the light will take 1 second to go from Earth to the moon. In 1 millisecond, it will go through the length of Switzerland, which is 300 kilometers. In 1 microsecond, it goes through 3 football stadiums. In 1 nanosecond is 1 feet, and in 1 picosecond is the width of the syringe, so almost nothing. And so basically, if we say about sub-nanosecond accuracy of synchronization, we mean that if the fiber that is if the 2 fibers that are connecting 2 devices, if they have different length of that means half a nanosecond. Okay. So just to give you some idea. So now, if it comes to evolution of synchronization needs, importance, and relevance in technologies and relevant technologies, synchronization is needed, even if you don't know, for operation of the devices that we use every day, like PCs, mobile phones, terminals for payment, and so on. Everywhere, synchronization is an underlying commodity that is needed. But this accuracy is 1 second, 1 millisecond at most that is needed there. In finance, synchronization is also needed. Up until the transactions were made by phone, it was not very relevant. But as soon as they became digital, the needs for synchronization were bigger and bigger. And there were 2 events that made it even stronger. The need is the regulation of audit. So in Europe is MiFID II. That requires 1 microsecond, I think, traceability. And then high frequency trading is another place where synchronization is needed to optimize the trading. Then telecom, again, synchronization is essential. Up until 5G, it was only frequency synchronization. But with the latest technologies and 5G, time and frequency is needed in the base stations to give you bandwidth to watch YouTube and so on. So to increase the speed of Ethernet connection. Now in power industry, synchronization is also needed at 2 levels. One inside the facility to monitor, and also between stations can be used for detecting faults. And up until there was only a power plant, and they distributed energy to all the customers in one direction, the synchronization was not so much important. But once we have now many sources of power that is injected into the grid, synchronization is more important to synchronize those. And also fault detection, because if you have if there's a fault on a line, it creates a spike. If you can timestamp the spike on 2 ends, and you can actually locate where it was and send immediately a group to fix it. Data centers, again, synchronization first was important roughly inside the data center with distributed databases for Meta and X and other services. The synchronization between the data centers became important so that you can correlate different instances of the same data. And then very recently, synchronization within the data centers became more and more important because it was realized that if the servers are precisely synchronized, you can optimize distributed algorithms which are run on many machines and basically make computations faster and make more money. And then in science, synchronization has been important for long because we are dealing with physical phenomena which happen at the speed of light, for example. So if in terms of technologies that cover the different needs, NTP is network time protocol, and you use it every day even if you don't know. And it provides synchronization at second millisecond level. Then we have GNSS. So this is GPS, Galileo, and so on. It provides synchronization from satellites, so you get time from satellites, but it's not always the case that you have the view of the sky. And also there's a number of limitations and problems with GNSS because it can be spammed, it can be spoofed, it can be jumped. So you might end up in a situation that you don't have reception of GPS. And also, if you want to go underground, then you cannot use GPS. You use PTP. So the alternative synchronization over network is PTP. And then we have White Rabbit, which provides sub-nanoseconds accuracy of synchronization. And as you can see, it became part of the standard, so the PTP standard, a profile of it. You can see here clearly a trend. So in many industries, the need for synchronization is more and more stringent, and closing more and more to 1 nanosecond. So again, White Rabbit, Genesis, it was created as a next generation control and timing system for accelerators. The project started in 2008, and the initial specs were to base it on well-established standards. We already saw it's Ethernet and PTP to provide sub-nanosecond accuracy of synchronization. There was also a need, and it's realized the deterministic data transfer, but we don't speak about this today. The initial specs were 10-kilometer links and up to 2,000 end stations. And importantly, it was to be plug and play. So we just connect the device and it gets sub-nanosecond without further work. It is open source and commercially available. Now, this slide is possibly the most important and more difficult because what I'm trying to do is in one slide to explain how White Rabbit works at quite simplified level. So White Rabbit is basically precision time protocol, layer 1 synchronization, phase detection, and asymmetry correction. And let me walk you through all of these components. So precision time protocol is a protocol that allows devices to be synchronized over network, and it works by exchanging packets. So one device, we call it master, is sending a packet, a message, and the transmission time is recorded. It's called timestamp 1. And the reception time of the same packet is recorded by the other device, the slave, which is timestamp 2. The same happens in the other direction. And in the end, we have 4 timestamps. And if we subtract T1 from T4, we know what was the kind of a round time. And if we subtract T2 from T3, we know how much it took for the slave to reply. So if we subtract these two values and divide by 2, we have a rough estimate of how long it took to transmit this packet from master to slave, even if the 2 times of the master and the slave are completely different, because you are just subtracting. So with this information, we can basically correct the time of the slave to be roughly the same like of the master. Now, this solution has some limitations. One limitation is that the oscillators of these devices in a classical implementation of precision time protocol, they are free running. And that means that essentially the counters that are ticking and providing the time, they might diverge. So even if you correct the time of the slave to the time of the master, it immediately starts being worse and worse. So you need to correct it again and again. And what is more, during the exchange of messages, it also drifts a bit. So if you care about milliseconds or even microseconds, you don't care about this phenomena. If you go to nanoseconds, it becomes important. Another limitation is the fact that we assume that that word is perfect and there is no asymmetries. So we just divide by 2 this round trip time, which is never true. So that also limits the accuracy. And the third thing is the timestamping resolution. So typically in PTP implementations, timestamps have a resolution of the underlying clock, which is 8 nanoseconds, maybe 4, maybe 16. And the best you could do is around 2-1 nanosecond. So the point is that you cannot get synchronization better than the resolution of the timestamps. So you will never get better than 1 nanosecond with timestamp resolution of 1 nanosecond. So we addressed all of these limitations. First of all, we use frequency transfer over layer 1. So if you are familiar with synchronous Ethernet, this is something similar to synchronous Ethernet. If you are not familiar, how it works is that when a device is sending data, it's sending bits that are encoded using a frequency. So automatically, the device that is sending data is sending also the information about at which frequency it is running. And this frequency can be recovered on the other side. But instead of Ethernet, it is basically discarded. So what we do, we actually use this frequency that is recovered from data to run the clock of the slave. And at high level, that means that both of these devices are running with exactly the same frequency. So their clock will not diverge. They will just keep incrementing the clock all the time at the same pace, even if the value of the clock is wrong. Another advantage of this solution is that the slave is sending its data with the clock that it received. So the master is sending a frequency and is receiving the same clock back. That means that the phase difference between the transmitted and the received clock is stable. In essence, what it means that we can measure the phase offset between these two clocks, and phase measurements can be very precise. We devised a method which is FPGA friendly that allows with very little resources to measure the phase at picoseconds level. Now we use this phase detection to actually increase the precision of timestamps. So we take the conventional PTP timestamps with a resolution of 8 or 16 nanoseconds, and we add the phase detection to make them picosecond precise. And once we have the precise timestamps, we can know precisely what is the round trip here. And the only thing that remains are all the imperfections of life in which are asymmetries. So what we do, we use one fiber for two-way communication, and that excludes the fact that the fibers can be of different length. Which, remember, if you have the difference of that, maybe more or less like that, is 1 nanosecond. And so it can happen easily that you will have different lengths of fibers. So if you use one fiber, the length will be the same. We use different wavelengths in two different directions, but this we can compensate for. Then we have a simple model for all other asymmetries, because the asymmetries can come from the PCB traces, which are of different length, of the FPGA internals, so a lot of places. We basically model it and calibrate. And with all that, we achieve synchronization on a link at the level of 10 picoseconds, and you will see it on the demo. Now you see the White Rabbit now, the devices, the future of White Rabbit. So in science, White Rabbit is de facto a standard. We had in 2018 around 500 devices deployed in different places. Currently, White Rabbit is deployed in 20 facilities and with around 10,000 devices all over the world. Alone at CERN and another partner, we are planning to deploy a few thousands of devices in the coming years. In industry, you can see this clear trend that the requirements are more closer and closer to 1 nanosecond. And we can see that White Rabbit as a service is possibly going to transition from national to international. And this is to basically replace or make a backup for GNSS. In financial sector, White Rabbit is becoming a trend as well, which you've seen. And we think that it will just take more. In other industries like telecom, we know that telecom starts to use White Rabbit. Very soon, there will be an announcement of one telecom company in one country using White Rabbit for operations. We work with power industry, and in quantum, White Rabbit is widely used. So once it becomes an industry, then White Rabbit will be used in this industry. White Rabbit was created by a small team at CERN. And once we had more and more applications outside of CERN, people asking more and more questions, wanting to use White Rabbit in more and more diverged applications, we started to hit a limit of how we can support the others outside of CERN. So we established White Rabbit Collaboration, which is a global fee-based, membership-based, you pay fee, a collaboration, which basically is meant to make sure that the maintenance and improvements of White Rabbit technology are at the highest level and also to the needs of the outside world, not only CERN. So we started this collaboration in March this year, and we so far have 15 members, and we will have more by the end of the year. LMS is the founding member here. We also noticed that different companies which produce wide area devices, they start asking, but how do we know that they work correctly? And also customers, how do the customers know that the device that they are buying, it provides proper performance? So we are working on compliance and certification with labs all over the world to be able to verify that wide area devices that are produced by companies, they provide the performance and compliance, and then for that they will have a logo, wide area logo. Training is important in the uptake of technology, of course. And that's it from myself. Thank you very much for your attention.
I'll do a very quick overview of ÜberNIC, and then I'll quickly focus into the precision time elements. So just to begin, ÜberNIC is an FPGA-based general-purpose Ethernet adapter. The network stack is implemented entirely in the FPGA chip. So MAC PCS, Ethernet core, IP, TCP, UDP, ICMP, IGMP, all are implemented in the FPGA chip. So this is not a TCP offload engine. It's not partial offload. This is complete 100% offloaded network stack operating in the FPGA. ÜberNIC supports PCIe 3, 4, and 5, and CXL 1.1 and 2.0. There are currently 4 different versions of ÜberNIC and 2 different board designs with 2 different FPGA chip options for each of the board designs. The smaller board on the right, which is what is on live demo today, has a single QSFP DD and 16 gigabytes of solder DDR. It is a single PCIe slot solution. The larger board on the left is also a single PCIe slot solution, but as you can see, is full height and 3/4 length. The larger board has 2 SODIMM sockets for memory, so a max of 64 gigabytes of DDR4, and it has 2 QSFP DDs for the network interface. Both boards will support 1, 10, 25, 40, 50, 100, 200, and 400G connectivity. For financial services, where we're primarily focused on globally as an industry, 1G, 10G, or 25G, particularly without forward error correction, the QSFP DDs can support up to 8 fiber pairs for 1, 10, or 25G. So we can put a 40G transceiver with a by 4 breakout cable, which is what is being used today in the demo, and we can have 4 10G fibers. We can put a 100G transceiver in and use the same by 4 breakout cable, and we have 4 25G fibers. Or we can put a 200G transceiver that emulates NRZ, and we can then have 8 1, 10, or 25G fiber pairs. There's a lot of other functionality, but I'm going to focus mostly now on precision time. So high-level precision time, we have implemented the 2019 version of PTP. So just general PTP with PPS-in capability. Of course, we support NTP, but I'm not going to talk about that anymore. We are here to talk about what we do in terms of the most performant precision time, which is first, White Rabbit, to synchronize time from an upstream device, a White Rabbit switch, to ÜberNIC. And so at that synchronization, we can synchronize ÜberNIC to the White Rabbit switch within a range of 20 to 80 picoseconds. Then within the host, because it's not enough that we're synchronizing the NIC, we have a host server that also needs to be synchronized. And as I think many people on this call recognize, one of the gigantic shortcomings of the current method of time synchronization is accurately and consistently ensuring that the host time is also properly synchronized. So again, step one is White Rabbit. The next part is what we call PTM, or precision time measurement, which is a relatively new mechanism that allows a time value to be transmitted across the PCI bus, using the PCI bus as a hardware update mechanism, not software. So that means PTM is highly consistent regardless of CPU load. I'll talk about that more in a moment. The last piece is what we call TGPIO PPS, or time-aware GPIO. On the 4th, 5th, and 6th generation Xeon CPUs, there are 2 pins. Those pins can be programmed to either receive a pulse per second signal or generate a pulse per second signal. So what we do is we can use the TGPIO capability to generate a pulse per second signal that is then transmitted to ÜberNIC, just on a normal coax fiber cable. And then we can compare the skew between the TGPIO PPS signal and ÜberNIC's own PPS. And once we identify that skew, now we know what the link delay is in the host itself. And once we know what that link delay is, we can compensate for that link delay to now achieve, again, 20 to 80 picosecond synchronization capability. So again, White Rabbit allows 20 to 80 picosecond synchronization between the White Rabbit switch and ÜberNIC, and the combination of PTM and TGPIO PPS allows for a similar 20 to 80 picosecond synchronization through to the host. So now, for the first time, we can consistently synchronize the host time to the network time on a server, on multiple servers in the same rack, on multiple servers in the same data center, on multiple servers across multiple data centers in the same country, the same region, or around the world. So it's a completely different level of capability. As a quick summary of the synchronization capabilities here, this slide shows White Rabbit PPS coming from the White Rabbit switch, which is in yellow, compared to a PPS coming from ÜberNIC, which is in the magenta. This is, as you can see, 76,000 measurements. The max skew was 266.7 picoseconds. The minimum, minus 250 picoseconds. Standard deviation, 63.57 picoseconds. And the mean, 4.88 picoseconds. No network card in the world supports White Rabbit other than ÜberNIC. No network card in the world is capable of this level of time synchronization. And again, that's where we start, and then we move the time value across the PCI bus and further optimize using PTM, and then further optimize using PTM. And I will cut my presentation short here because
Adam, I think you need to explain here.
Okay, so I will show a quick demo. In this demo, you will see the core devices that are used in the White Rabbit network, which are White Rabbit switches. In contrast, what Seth was just explaining is one of the nodes, for example, ÜberNIC, which is actually connected to White Rabbit network, and then it's getting timing and synchronization from White Rabbit network. So what I will show you, there are 2 switches connected together first with short fiber with 2 meters fiber, and then I will switch to a much longer fiber to 10 kilometers, and okay. And then meanwhile I will show you on oscilloscope the 1 PPS signal, so pulse per second signal generated by both switches, and we will see when those switches are synchronized, the signal will be very close. And maybe I will. Okay, and then after that, I will show you a demo with Hor Edgan. I will show you the same synchronization over a 10-kilometer link, and then I will disable White Rabbit tracking on one of the switches. I will heat up the roll of fiber, and you will see that those devices, they are not synchronized anymore. And then I will enable again White Rabbit, and you will see that those devices are able to synchronize back. So okay, so what we need to have a synchronization using White Rabbit, we need two devices, two let's say White Rabbit devices. What we have here, we have two White Rabbit switches from different manufacturers. And right now, I will use short fiber, the 2-meter fiber, to connect those two devices. As I said before, it takes let's say 40 seconds to 1 minute to have it synchronized. And have a look over here. Let's see. Is synchronizing almost. So what we see on the scope right now, we see only one signal from the bottom device. This is 1 pulse per second, and when the devices are synchronizing, we should be able to see the second signal. So what you can see on the scope that the PPSs from both devices, we are synchronized within, I think, like 100 picoseconds, roughly, or maybe even better. So what I would like to do now is to replace the fiber, the 2-meter fiber, with a much longer one, with a 10-kilometer fiber, which I have here on the roll. And with this much longer fiber, we still expect to have the same results. So the PPSs, they should be aligned still within like a tenth of picoseconds. And once the devices are synchronized, it doesn't matter. I mean, over time, they should be kept synchronized all the time. So the synchronization doesn't improve with time passing. So it's like once they are synchronized, then they are synchronized. Okay, so they are synchronized. So we see that the PPS signals, they are one over the other. And now what I would like to show you, so already what you saw, that it doesn't matter how long the fiber is. With short fiber, we are able to get the synchronization, but the same is with much longer fiber. So with like 10 kilometers, as you see here. So right now, I will disable the White Rabbit on this link. So right now, those two devices, they are running with their own oscillators. You see that they are still synchronized, but over a time, the synchronization will diverge. And to speed it up, I will use a hard dryer to warm up the fiber. It will cause that the fiber will become a little bit longer, and those clocks of the devices, they will diverge. So as you see those PPSs, they already diverge. It's probably really hard to see on oscilloscope or on the screen. But let's say this length is about 400 picoseconds. So right now, those two signals, PPSs, they are apart like 200 picoseconds. So what I will do right now is I will enable back white rabbit. So those two devices will synchronize again. So as you see, they are in sync again. Okay, thank you. So that was the first demo, and now Seth will continue with ÜberNIC.
Okay, so we'll finish up the presentation with a quick live demo of ÜberNIC. So to describe what you're looking at, this is a white rabbit switch with a management port connected, with a pulse per second out cable, and with a 10G fiber pair into port 2 on the white rabbit switch, which connects to ÜberNIC as fiber pair 4. The server itself, this is an ASRock prototype Xeon Gen 6 motherboard with a Xeon 6th generation engineering sample of a Sierra Forest E-core or efficient core CPU. And we have two different ÜberNICs plugged into the server. One is programmed as Taser for network I/O simulation. This second board that I'm pointing to is actually running as ÜberNIC itself. There's a very small cable here. This is a pulse per second out from ÜberNIC. And there is also, this is a little harder to see, a pulse per second out from the motherboard. So this is TGPIO PPS. So these three PPS outs, again, one from the white rabbit switch, one from ÜberNIC, and TGPIO are all coming into the oscilloscope. I realize it's a little difficult to see. But again, what this is showing very quickly, high level, is ÜberNIC as a precision time enabled general purpose Ethernet adapter, synchronizing time to the white rabbit switch with the peak with, sorry, I got to look and see what the precision is right now. With precision of, I can't quite see, it looks like 76 picoseconds of standard deviation. Sorry, not wearing my glasses. So you can see the accuracy of this here. The white rabbit PPS is the yellow line. The ÜberNIC PPS is the magenta line. And the blue line is the TGPIO PPS from the motherboard, which, as I described, because the TGPIO PPS is driven by a crystal clock that's driving an always running timer, and the clock is at 25 megahertz. So there's a bit more jitter in the TGPIO PPS. That's just simply a function of the architecture of the CPU. But you can see the results here. Again, this is live and running, and this is a white rabbit end node in the form of a general purpose Ethernet adapter. And again, this is the only Ethernet adapter production ready in particular that supports white rabbit. So as I said earlier, and as you can see, this is 20 to 80 picoseconds of synchronization between the white rabbit switch and ÜberNIC. And again, ultimately 20 to 80 picoseconds of synchronization through to the host. And that is it for our presentation.